today talk. And today we have guests from the University of Toledo, Dr. Trieu. Um, Today his talk is about m-Isometries and their properties. Thank you for being here, and then thank you everyone.
All right, thank you very much for the introduction, and I would like to thank Hoa for the invitation. Um, the talk today is about certain class of linear operators, and you will see throughout the talk there's some familiar things from linear algebra class. Um, so first, uh, maybe not many of us have heard of m-Isometry, right? But it turns out that all of us, um, I think so, all of us have seen them. We just don't know the name. Uh, um, so to begin, I would like to let me see how I move it down a little. I think okay. So sometimes it's the mouse is not moving well. So let me just try to see what happens. How do I do this? Okay, so maybe this. So to begin, I will give some introduction here. So throughout the talk, CN will be the usual Euclidean inner product space and norm. So working with the complex variable. But if you could think of real numbers as well, okay, n as well, instead of in that case, then instead of complex values, they are real values. For the purpose of following the talk, is okay. So let me recall that whenever we have an n by n matrix, then we can associate to such a matrix a linear operator by standard multiplication. So for example, if we have T is like a matrix n by n, so a 1, 1, 1, 2, etc. like this, 1 n, and then 2, 1, 2, 2, etc. Then for each vector v above, we can associate a new vector by writing the v in the column format, and then we just do the matrix multiplication. Okay? Then we have a new vector here in the column format, and then we consider this as a vector in Cn, and that the standard way to define a linear operator given a matrix T like this. So all of us are familiar with the notion of isometries. Those are linear operators that preserve the norm, preserve the length. Right? The length of the image is the same as the length of the input or the original vector v. So what are examples of isometries? From linear algebra, right? We something like this. Any diagonal matrix of this format, where the entries on the diagonal have absolute value 1. Whenever we have such a matrix, then T give us an isometric operator, an isometry. And it turns out, by a result in linear algebra, any isometry on Cn looks like this, looks like the above format after we change the basis. Right? It's known as something like diagonalizing operator on Cn, or also the spectral theorem for linear operators on Cn, something like that. So in particular, if all of the entries here are just one, then we have the identity matrix. So the identity matrix is the trivial isometry. However, if we change the identity matrix just a little bit, then we don't have isometries anymore. And especially if we look at those Jordan blocks like this. So simple Jordan block with ones on the diagonal. So such Jordan blocks are not at all isometry. They don't preserve length at all. However, they satisfy something quite interesting, satisfy interesting conditions, which I will discuss in details as follows. And in fact, in general, if we have an identity and we add a nilpotent matrix, so nilpotent, and we recall that nilpotent means that if we raise n to a certain power, then we get 0. Let's see what it means, nilpotent. If we add a nilpotent to the identity matrix, then the resulting usually is not isometric. You can think of nilpotent operators or nilpotent matrices as say strictly upper triangular or strictly lower triangular. Those are nilpotent. So even though the above matrices do not give rise to isometric operators, they do satisfy something interesting, some equation, some interesting equation. But let us consider the simplest case here. You see the Jordan block, T equal to identity plus this nilpotent matrix. This is strictly upper triangular, right? So let us do some calculation to see what happens. So we consider T as acting on C2, right? It's a 2x2 matrix. And for a vector, say for V, two components, say X, Y, on C2, X and Y, each of them is a complex number. Then if we compute T of V using the matrix multiplication we have earlier, we need to write X, Y in the column format, right? And then we will have so 1, 1, 0, 1 like this, and then X, Y. And if we compute this, but then we need to rewrite the new vector in the row format. So to be more precise, let me just write this transpose of this. So when we use matrix multiplication, we do we write the vector vertically, but when we write out the vector, we use row. So it's like X plus Y here, and then Y. That is the action of T on a vector V. Now, if we do one more time, we have T squared V. Then with the same calculation, we will have X plus 2Y, comma Y. One more time, T cubed. Then we will have X plus 3Y, Y. Right? Of course, you can see the parent, the familiar parent because of the Jordan block, X plus Y, X plus 2Y, X plus 3Y. But an interesting thing we can realize is that follows. If we compute the norm of of all the vectors we have done so far, the norm square and the length. So it's going to be absolute for v, it's going to be absolute value of x squared plus absolute value of y squared. Okay, and then for TV, we have this absolute value of square plus absolute value of y squared. So it becomes, you expand it, it will become something like this: x squared plus x bar y plus x y bar plus y squared, and then there's another y squared. So I have actually two absolute value of y squared. That is the length of TV. Similarly, if we compute the length of t square v, so I'll just write out here for you. I have calculated in the my note. It looks like this: x y bar plus 5 absolute value of y squared. And one more time. So please bear with me for this tedious calculation. But the thing is, I want to show you that from this calculation, we can get something interesting, which we may have not realized before. So it looks like this for t cubed. And this is 10 y squared. Right. Okay, so by looking at this, it turns out that the following is true. If you take this and you so t cubed v square, you subtract 3 times this row. And then you add, so this is like minus 3, and you add 3 times TV, and you minus this. Then it turns out you get 0. So for example, right, if we take this, subtract 3 times, plus 3 times, and minus this, we get 0 because they're the same. But this is the same thing here, right? 3, and then we subtract 2 times 3, so 3 minus 6 plus 3, right? That's 0 again. And like for this one, we have 10 minus, let's see, 15 plus 6 minus 1. So if I do my arithmetic correctly, this is also 0, I hope. Yeah. So interestingly, by combining these things, we have a nice equation that the operator T satisfies. And we should notice that the coefficients are familiar, right? The coefficient here. So I want to make the highlight. What doesn't work? Okay. So let's go back here. The coefficient, they see 1, and then minus 3, and plus 3, minus 1. Those are the binomial coefficients. We call such an operator T a 3-isometry. The reason for the 3-isometry is that we have these 3 power here, right? And we use all the power, power 3, power 2, power 1, and then this is power 0 for T. And the coefficients comes from the binomial expansion for t minus 1 cubed. And those coefficients come from the expansion of this. So in general, whenever we have a linear operator that satisfies a similar equation, but instead of 3, we have an m here. Then we say that T is an m-Isometric. So T is an m-Isometric operator, or just an m-Isometry. An m-Isometry. So we have the m, and then we have the binomial coefficient, and for t we raise to the power, right? K run from 0 to m. So we have v, and then tv, and then t square v, etc. And the coefficients come from t minus 1 to the m. That's where the coefficients come from. Come from this. So we see that our first Jordan block, the simplest Jordan block above, is a 3 isometry. It turns out that similar thing happened to other Jordan block as well. In generally, whenever we have an identity matrix, this is I for identity, and we add a nilpotent, right, then the sum is always m-isometric for certain value. It depends on the degree of the nilpotent. Okay, what is the power we need to raise to n to get 0? So my encounter, or maybe my motivation for studying m-isometry was quite accidental. Back in 2013, at a certain day, I was browsing through papers newly published on the Journal of Mathematical Analysis and Application. So when I have some time, I have the habit of just looking through though to see what, if anything, interesting to me. So I saw a paper by Bermudez, Martinez, and Noda, these Spanish mathematician. And in that paper, they prove the following. They prove that if we have S, we begin with S and isometry. So before we saw identity, right? But identity is just a very trivial isometry. In the theorem, they have general isometry. If we begin with S, a general isometry, and N is the nilpotent of order L. So meaning that N to the L equals 0. Okay? And L is the smallest number that satisfies the condition here. So S is an isometry, N is a nilpotent operator, and they commute. S and S are the same. Then the sum of S and N is always m-isometric. But this m, particular m here, depends on the order of the nilpotency of n. M is 2L minus 1. So in particular, right, if S is the identity like above, then we have 1 plus n is 2L minus 1 isometric. So I thought it was interesting result. I haven't, at that time, I hadn't seen isometry before, and it's kind of cute because you begin with something very familiar, and then you add something nilpotent, and you get some, it's not isometric anymore, but it's something related. It's quite interesting, and that's why it caught my attention. So I look at the proof, but it's the proof looks quite complicated, and they use certain binomial or combinatorics identities, and that maybe that the natural approach, because if we go back to the example again, if we try to, instead of the simple example that I did, if we try to do something more complicated, like this or the other one, then maybe we need some combinatoric identities involving the binomial coefficients, for sure, right? If we try to calculate. So because I like the result a lot, but I didn't like the proof because of the manipulation of combinatoric identities. Now, I do like combinatorics, just for a fact. Okay, I like reading and like doing that, but I just don't like using complicated identity to prove this fact. So I was trying to come up with a different proof, and luckily I succeeded, and that's why I got interested in the theory of m-Isometries here. So yeah, these examples again. This we see that the three isometry. For this one, we have the identity at a nilpotent. This nilpotent has order, I believe, order 2, because we need to raise to order 2 to get 0, I believe. No, wait a minute. I think this one, the nilpotent is order 2, but for this nilpotent, if we raise to power 2, we get a 1 in this corner, so we need to raise to another power to get 0. So the nilpotent is of order 3, and because of that reason, the sum here is a 5 isometry. It satisfies the equation corresponding to m equal to 5. For this one, the nilpotent is just the 1 on this corner. So when we raise to power 2, it's already 0. So still, this is a 3 isometry, according to the result above. So moving forward, let me just explain, just tell you some literature on m-Isometry. So after I got interested and I looked at the literature, and I found out that people have studied isometry for a long time. So isometry was actually introduced and studied by one of the well-known operator theorists, Jim Adler, in his paper in 1990. And in 1995, Adler and his students, Tankers, published a series of 3 papers on spectral properties, representations, and many other things on m-Isometries. So the series of 3 papers is quite thick.
I think Jim Adler is from the University of Washington, right?
You mean currently? I think currently he's in San Diego, but what he may have connection with because Jim Adler and then McCarthy. McCarthy was another well-known operator theorist, and
McCarthy is from
Washington.
Yes,
Washington University in St. Louis. Yep. But yeah, Jim Adler and McCarthy have written several papers together, and they have collaborated with each other a lot of time. And there are other works in m-Isometry as well. But most of the works before the paper by the Spanish group were about spectral properties, carefully more like deeper results, more difficult results. But the algebraic properties that we have just seen, right? Adding a nilpotent to an isometry, those algebraic are multiplying m-isometries together, which I will discuss next. Those things have attracted attention just very recently. That's what I have found out. So, but first, let me just give you a kind of like a taste of what these m-isometries are about by giving you some basic properties. First, eigenvalues of these. So suppose we have T is an M isometry. So it satisfies that equation, operator equation. And say we have an eigenvalue, right? Say T of V is say lambda V for some V different from 0 and some lambda. What can we say about, is there anything we can say about lambda here? So a calculation, right, if we have TV is lambda V, then TKV, right, if we apply TK times to V, then it's just lambda to the K V. Then if we plug into the equation for m-isometry, so remember m-isometry means that the sum here, right, K from 0 to M of the alternating sum, M minus K, and then the binomial coefficient, M, K, and the norm, T to the K, V square. The sum here should be 0. But from the calculation, because V is an eigenvector, this just give us absolute value of lambda to the 2K times the norm of V square. Right? So all the terms in the sum have the factor of V squared. So we can just factor that out. And we have something nice. And this is K equals 0 to M of the alternating binomial coefficient. And over here, we have absolute value of lambda to the K. Right? But then we realize this is just exactly the expansion of lambda square minus 1 to the power m. Right. So the conclusion is that because the vector v should be non-zero, the conclusion is that lambda square minus 1 to the power m must be 0, or equivalently, absolute value of lambda must be 1. So all eigenvalues must have absolute value 1. All of them must live on, must lie on the unit circle. So this is something interesting already. Eigenvalues must be on the unit circle for m-isometry. Now another property is when we look at the action of T on a certain vector V. So recall here again that if we have an m-isometry, then this is true for all vector V. So in particular, if we replace V by Tn of V, right? For each n, we replace V by Tn of V. Then we have a new equation here, which is also true for all n we use and all V. But this tells us that the sequence of norm, oh, I should make a typo. This is square. The sequence of TVN square is a recurrent sequence. Satisfy a recurrent satisfy this sequence. Satisfies a recurrence equation, recurrent relation and relation. That is the recurrence equation for this sequence. And this is related with combinatorics, right? And whenever we have a sequence that satisfy a recurrence equation, then to find out the formula, we can use the characteristic polynomial. And in this case, because the coefficients come from the expansion, the binomial expansion, the characteristic polynomial is just so the characteristic polynomial is exactly the one that I wrote earlier, t minus 1 to the n. So when we solve this characteristic polynomial, we have the roots of 1 repeated m times. And from the theory of recurrence relation, it follows that the sequence, the TNV square, is a polynomial in n, a polynomial in the power n here, of degree at most n minus 1. And this is the necessary and sufficient condition for a linear operator T to be an m-Isometry. For any fixed V, Tn of V taking length and square it is a polynomial in n. So as a consequence, it's easy to see that if T is m-isometric, meaning that the sequence here is a polynomial in n of degree at most m minus 1. So in particular, it's of degree at most m plus 1 minus 1 as well. And that's why the operator T, whenever it is m-isometric, is also isometric with higher degree. With m. If T is m-isometric, then it's also m plus 1 isometric and so on. So higher degree, but going lower is in general not possible. However, in the case T is invertible, if 1 to 1 and on 2, from the definition of m-isometry, we can actually see that any m-isometry must be 1 to 1. It doesn't have the kernel must be 0. But in general, if we look at finite dimensional, then yes, T will always be on 2. So it's invertible. But if we look at infinite dimensional, I haven't talked about infinite dimensional, but we could do that as well. For infinite dimensional operators, then there's no guarantee that T is invertible. But if T is invertible and it is 2L, if we know that it's an even like this 2L isometric, then we can actually reduce the degree by 1. So in finite dimensional, the smallest m for T to be m isometric is always odd, right? Because if even, we can reduce by 1. And that's the reason why in the previous example, we only saw 3 isometry or 5 isometry. We don't see 4. Well, we do have 4, but 4 will reduce to 3 anyway. Because anything in finite dimensional when it's the m-isometric, it must be invertible. The idea to see this is as follows. It's also from the characterization using the sequence. It's a little bit more involved, but the idea is as follows. In the case the operator is invertible, then it turns out that TNV here is also a polynomial in n for even negative values of n, right? For even negative integers. So if something like this is a polynomial of n for even negative integers, and because the whole thing here we square it, we take the norm and square it, the polynomial should be non-negative. Right? So the polynomial must be in order for it to be non-negative for all negative integer, the degree of the polynomial must be an even degree. Must be an even degree, and from there we have the m should be odd, right? Because the degree of the polynomial is m minus 1. That's roughly the idea. But well, I think I have only some time left, so I want to talk about the approach that I have in order to prove the above results in a better way, in an easier way, but we're also able to obtain more general result. So this is the result I obtained in 2015, and it turns out that other people, including the Spanish group there, prove this as well independently using different method. So we begin with S, now an m-isometry. Recall that in the original result, they just have S at an isometry, but here we allow m-isometry. And n is nilpotent of order L as before, and they commute. Then the sum is m plus 2L minus 2. In the case of isometry, m equal to 1, and that's why we have 1 plus 2L minus 2, which is 2L minus 1. But in general, we need the m there. So we could imagine that if one try to use combinatorics identity to prove, it's possible, but it would be complicated to do. So here's my approach. Make use of the following ingredients. First of all, instead of just one variable, even though it looks like one variable, right? Because we talk about the sum here, which is a single operator to be something isometric. It turns out that it's easier if we split the two variables, like the hypothesis, two variable s and n separately, and then we combine them. So working with two variable seems to be more beneficial. Right? Of course, it would be nice if we do we teach students several variables first, but that may not be a good idea in calculus. Right? And then we use something called hereditary functional calculus, which I will explain. And then the elementary theory of polynomials, basically just binomial expansion. So to begin, to show you the ideas of my approach, let me recall again the definition of m-isometries. Right? So T is an m-isometry if these things equal 0. But using the inner product in linear algebra, this can be written as a TKV inner product with TKV and then we can bring tk to the other side, and we get the conjugate, the transpose, the conjugate transpose. So that is the t star, that's the conjugate transpose, and then t v v, and that's what we have here. So because this identity must be true for all v, this operator here, the combination of several powers of t, must be 0. And this is the operator equation for m-Isometries. Instead of talking about v, the equation with v for all vector v, we just have a single equation, operator equation for t to satisfy. So we're gonna make use of this operator equation instead. Now, the hereditary functional calculus by Jim Ackler, he introduced this in a different paper, not on the study of m-Isometry, but in different paper. But they also use functional calculus in the study of m-Isometry for sure. That's before it's beneficial to consider two variables. So let me use the general, the standard notation C of this to denote the ring of polynomials in two variables with their conjugate. And say we have two operators A and B that commute, and we put it into a tuple like this, a pair like this. Then we can define a linear map from polynomials to operators as follows. Any polynomial, it's a little complicated, but basically it's just a linear combination of these monomial. Right? So any polynomials in z bar, w bar, z w, it's just linear combination of these things. So I'm gonna define a map as follows. These things just go to this operator. So when you see z bar, you replace by a star. That's the conjugate transpose. W bar replaced by B star, and then Z by A and W by B. That basically we define the linear map. Keeping in mind that the star should always be on the left side, and with the operator A and B on the right hand side. This is called the functional calculus for polynomials. There's a general notion when we may allow what more general functions, analytic functions, etc. But for us, polynomial will be good enough. So that's how we define the hereditary functional calculus. Now on this side, because A and B commute, so we really don't care whether we write A first or a gamma, a to the gamma, b to the delta, or b to the delta, a to the gamma, the same, and the same thing here. But we need to make sure that the star, the actual conjugate transpose, must be always on the left. So why this is important in the study of our m-Isometry? The reason is that if we begin with a polynomial p as z bar z minus 1, then from the definition or from the operator equation for m-Isometry, we have the following fact, that S is m-isometric even only if when we raise p to the power m and then we apply the hereditary functional calculus, we get 0. Okay. The polynomial here has only z, it doesn't have w, so it doesn't matter what we put in here. Okay. So no, it have no effect on when we use the hereditary functional calculus, because p to the m doesn't have any w in it. Okay. So that's why it's important. And in the case, say if we take Q to be W, then an operator is nilpotent, n to the L equals 0, even only if, I think there's a typo, there's Q to the L, right? Q to the L applied to this tuple must to this pair must be 0. So in this case, Q doesn't have any Z, so there's no effect for the first component. Now, an important thing to keep in mind about this hereditary functional calculus is that it's not multiplicative. So if we begin with two polynomials and we multiply them together, then usually it's different from PT and TQ, like that. So remember, the reason that for this, right, all the T star must be on the left, and then the same thing for the Q, all the T star must be on the left. So when we multiply together, we will have both, right? T star on the left and T star on the right of this. Okay, so for example, we have something like this. So this may have something like T star T. No, sorry, A star A. And then on this side, it may have something similar. Say A star square A. So when we multiply these two, then we have A and then A star square. Right? We cannot move the A star to the left because A and A star may not commute in general. So that's why when we multiply these two, we may not get f times g applied to the tuple. However, you can see that if I multiply three polynomial, and this R here is conjugate analytic, meaning that it has only Z bar and W bar, and this on the last components only Z and W, then we do have the multiplicative property, right? Because when R has only Z bar and W bar, then when we apply the functional calculus, RT has only the star, the conjugate transpose. And then on the other hand, Q has only the original operator A and B. So when we multiply them, it matches the definition of hereditary functional calculus. Another simple to verify but important is this. If we look at all the polynomials for which the functional calculus apply, the hereditary functional calculus apply to the tuple, to the pair T V equals 0, the collection of all such polynomial is an ideal. So even though usually in if you from abstract algebra, right, if we have like a map that is a ring homomorphism, so it's linear but also it's a multiplicative, then the kernel is an ideal. Right? Over here, it's slightly different, that the map is not multiplicative, but surprisingly, it's easy. It's not difficult to see, but surprisingly, the kernel is also an ideal, and that's the reason why my arguments work in order to prove the result. So this is the result, and there's only a few minutes left. I'll just quickly give you an overview of how to prove this. So again, the hypothesis is that S is a m-Isometric and it's nilpotent. So n to the L equals 0, and then S and n commute. Then the conclusion is S plus n is m plus 2L minus 2 isometric. So how do we do that? We use the hereditary functional calculus. We make T to be this pair, S and N. Remember that S is m-Isometric, and then this N is nilpotent. Right. And we look at the collection of all polynomials P for which P of T equals 0. We know that this is an ideal. Right. Now, what do we say about this ideal? What do we have in that ideal? Right. By the assumption that S is m-isometry, we know that this polynomial 1 minus the absolute value of z square, or the same as z bar z, is in that ideal. Right? And then n is nilpotent of order L, so the WL is also in that ideal, and then W bar L is also in that ideal. What do we need to prove? Right? We need to show that S plus N. We need to show that S plus N must be this. So we need to show, in terms of polynomials, we need to show that this S plus N is represented by W, Z plus W. So what we want to show is that 1 minus Z plus W square to the power M plus 2L minus 2 belongs to the ideal as well. Right? So if we have this, then it implies the conclusion. Because remember that in the hereditary functional calculus, we replace Z by S and W by N. But then it just boils down to doing calculation with polynomial. Right? And the idea to do so, you just expand it out. Actually, just do to expand this, we have Z bar Z, and then Z bar W, Z W bar, and then minus W bar W. We want to show the whole thing here. 2L minus 2. We want to show this belong to the ideal. So try to write down this, right, as the combination of these things. So we can write out this as a sum involving 1 minus Z bar Z to the M, and then WL, W bar L. It's just using binomial or multi-monomial monomial expansion. And this is simple enough to do so. So our works also give us a result in a more general setting like this. So if we begin with an operator S satisfying certain hereditary equation, more complicated hereditary equation, and if we have N is a nilpotent commuting with S, then when we take the sum S plus N, the result also satisfy a similar equation with the appropriate order here. So it looks like that. Go to that order. We add 2L plus 2 to each exponent. And so I have a few more things, but other than that, that's enough. So I'll just say thank you for your attention, and I hope you enjoy the talk.
Yeah, thank you very much, Dr. Lê. I think the talk is very interesting and very clear.
Thank you.
And now let's wait for questions from the audience. Do you have any questions for our speaker? Today we have very good, audience, like the number of participants
Oh,
32. Yeah.
oh, thank you. Thank you for coming.
Do you have any questions for Dr. Lei? I don't hear, but I have a couple of questions. So,
Oh, okay.
yeah, would you please go back to the theorem in 2015?
2015. Yeah.
Yes. No, the previous one.
13, right? The original one.
Yeah, that might be the original one. But yes, this one. So
Actually, the
I
same
just
thing.
wonder
Yeah.
the condition, commutativity Sn and Snn.
Right.
So like, yes, this condition is very strong. So
Mhm.
can we just make that weaker a little bit? For example, S is commuting with like n to the m for some power m.
That's a good question.
So like, for
So
example, Sn square equal to n square s. How
yeah,
about that?
yeah. That's a good question. So the thing is, at least with my approach, I don't see how it works yet, because the approach we begin with the hereditary functional calculus, and in order to define the hereditary functional calculus correctly, we need the two components to commute in order to do so.
Yeah.
But it's a little tricky um, because eventually, because n is nilpotent, so eventually n to the l must be 0. So then s commute with n to the l. but
Yes, but
but
the weaker condition
right,
do
yeah,
not imply.
right. So that yeah, I don't know. But we know for sure. We know for sure that if there are examples that if S and N do not commute, then the sum will be very wild. We have no idea.
I see. I
There's
see.
no control on the sum. So we do need commutativity to get some result like this. But yeah, what under the weaker condition like S commute with a certain like n square, then
Yeah.
yeah, I'm not quite sure. What
Because when S and N are commuting, S plus they can be diagonalized by the same
yeah,
unitary.
for sure. Yes, yeah,
Yes,
that's a very
yeah, that makes
good
the
observation.
maybe the problem easier to prove.
Yeah, right. No, so on the other hand, here it works for even infinite dimensional operator as well. But yes, I agree that in the case of finite dimensional, there can be simultaneously diagonal. Kind of well, can be simultaneously put into upper triangular form. Right? That
Mhm.
might be a better way to say, because in general, well, for n, right, it's not going to be diagonalizable. Um, uh, it's nilpotent. So um, but also, there's another thing that we need to be careful, because in the definition of m-isometry, it would just use similarity. It's not enough. Similarity will change things, but if we use similarity via unitary, then it works. But if we use similarity, so by similarity, I mean you multiply by p and then p inverse, right? Then we do need p to be need p to be unitary
Mhm.
in order for it to preserve
Yes.
m
Right.
isometry.
Yeah.
Yeah, but yeah, it's an interesting question that you asked. But I haven't talked about that.
Yeah. In general, that might not be the case, but maybe for some, if n, for example, n square is commuting with the s, you might
Mhm.
use that to control the situation with n plus n, s plus n.
Yeah, yeah, something of that type would be interesting. Yeah, I don't know. Or something we can require the commutator as an the commutator
Yeah,
to
the
be
commutator
small or
is just
something,
zero in
right?
this case.
Yeah, or the commutator to be something, right? Can we do some with this? Yeah. not zero, but something, right? That's another question.
Yeah, I remember when I studied some similar problems like sum of squares for matrices and even for trace,
Mm.
like commutators and plus sum of squares,
Uh-huh.
something like that. But the condition of commutativity is very strong. Yeah.
Right, right.
Yeah. I have one more question regarding the number, the m isometry. So
Mm-hmm.
you said that if the m is even, so you always can reduce to just reduce the m by
One,
m to m
right.
minus one. So
If
how about
it,
the reverse? Can you go from m minus one to m?
uh no, no, yes, you can always you can always increase.
Oh, really?
Yep. So here that the right here. So if we have m isometric, then we can
Okay,
always
I see. I
increase.
see.
But reducing is harder to do,
I
right?
see. I see.
In the case of invertible, then we can reduce from even. Now, in the case um, if it is invertible and we have an odd number to begin, then we in general we cannot reduce more. Uh, uh,
I see.
but
I
even
see.
we can reduce in the case of invertible operator. So in finite dimensional space, when we talk about the smallest number m, then it will be always odd uh, in finite dimensional. Uh,
Mhm.
but for infinite dimensional, I think I didn't have time to talk about that. But maybe I'll just show you that there in infinite dimensional there's a so-called the Dirichlet shift,
I see. I
like
see.
this. Okay, we shift with certain coefficient appropriately, then it turns out this is a 2 isometry. So it's an even number here.
Mm,
Isometry.
I see. Okay. Yeah. Yeah. I would like to thank you again for interesting talk.
Thank you for
And
having me.
thank you, everyone. Right now, we still have 32 people. So actually, they are really patient.
Yep, thank you. And I noticed there's some Vietnamese name that you're currently in Vietnam now. It's near
Yeah,
midnight.
some of them are from
Yeah,
Vietnam. Yeah.
yeah. So thank you very much for attending during the night.